introduce Jim Carroll. He's editor of Optical Networks Daily, covering next generation networks with a focus on optical, silicon, and software. He's also the editor and founder of Coverage Network Digest. Jim?
Hi, everybody, and welcome to our webinar on silicon photonics co-packaging with IBM Canada and GlobalFoundries. This is actually the second in a series of webinars that's sponsored by DuPont's Silicon Valley Technology Center and the Consortium for Onboard Optics, or COBO. We're having about one webinar per month. Information on our October webinar will be posted shortly. So our guests today are Alexander Yanta-Polzinski, who is a senior engineer at IBM Canada, and Vikas Gupta, Director of Product Management at GlobalFoundries. So with that, let's get underway. Alex?
Thank you, Jim. Hello, everyone. Thank you for joining us today. So I'm Alexander from IBM Canada, and today we will discuss about efficient manufacturing of photonics and electronic and co-packages. So I would like to thank you, Jim and Melissa, for organizing this event, and DuPont for sponsoring it. So first, who we are. We are IBM Bromont. We're the largest North American-based semiconductor assembly and test. We have over 850,000 square feet of manufacturing floor. We specialize in advanced packaging, mostly doing flip chip and photonics. We can assemble any wafer source. We're master of complexity. We also have outstanding characterization capabilities. We have a world-class FA lab. And we, of course, can help in design for manufacturing and better time to market. And to do so, we also have a development dedicated facility where we can develop our new processes and your new product introduction. And when they're ready, we can mimic and copy those line and process to the main production floor for rapid scale up. So the kind of industry, for 1/3 of our production is for IBM products and crown jewel. But we also have 2/3 of our production is for more OEM business that goes in high performance calculation, data centers, telecom. So for example, we build mainframes, we build antennas, phased array antenna for the 5Gs, antenna controllers, transceiver, all the components for high performance computers. So we can be involved in that. So this is kind of the projects we manufacture. If you look at advanced packaging that's behind those kind of projects, for the top left, you have this large single chip module. This is a 23 by 28 millimeter chips with over 20,000 C4 connection on the laminate. And then we can go to higher complexity where multiple chips and integration and system and package can be done. We also do custom design. We also have coreless, where you remove the core in the PTH, so it has better cost and electrical advantages. And of course, we do chip scale package, 2.1, 2.3, 2.5D, 3D packaging, and photonics. And today we will discuss how to include those photonics close to an ASIC or logic chip, electrical chips, and what is the best way to manufacture those. So here are some photonic co-packaging demonstrator that we have built in the last years. So first we have this high fiber count application that you can see on the top left. So this is a large ASIC chips where 9 silicon photonic loopback chips were placed. And the main goal of this test vehicle was to monitor if the silicon photonic chips and the optical interconnects were able to withstand the downstream process to completing the module assembly. Then at the middle of top, you have this higher density optical package where we use our polymer interconnect technology. So I have highlighted it with some colors here to show the polymer to photonic chip adiabatic coupling area, and also where the polymer lies inside the ferrule and how it's made to the system ferrule. We also have this integrated connector. So here you have a top view where a metallic spring clip will make the 2 empty ferrule with the correct load force. The bottom left, you have a solder removable silicon photonic fiber assembly. You have a better view here of how it's made and with the strain relief of the pigtail. And of course, the full optical switch demonstrator that we have published this year. So our vision for silicon photonic packaging is to get away from this active alignment, one connection at a time of custom design, and do something that is more scalable, and it can lower the packaging cost, because as you know, integrated photonics, the packaging and the tests dominate the cost structure. And this is very difficult to overcome, because the component and the alignment, the tight alignment requirement of single mode optics make it very hard. So our main vision is to automate it in high volume, and using self-alignment and doing multiple connection at a time with a standard design will leverage the scalability of the packaging. And this is leveraging the microelectronic packaging infrastructure and know-how. So this is our vision. Our vision also include more collaborative or ecosystem that bring all everything to align for success. So I will present very quickly some of the Northeast microelectronic corridor that can benefit this industry. And this ecosystem enables research and development to full volume manufacturing. I also have to mention that we closely work with a lot of IBM research sites, and this makes my job really exciting, because those research center develop those new technology, and typically will contribute on making them manufacturable. So this is very interesting for us to be at the leading edge of the advanced technologies and make them manufacturable. It's a very, very high privilege for us. So I will just, in the next few slides, I will show some of the actors can be a good introduction to this technology of photonic packaging, and I will explain a little more. First, there's the C2MI. This is a center collaboration with IBM as a founder with Teledyne DALSA. It's an incubator center when you can do first level prototyping, and it is really the development center that we were presenting in the first slides. So there you can do your prototypes or process development, and C2MI is a great infrastructure to do this integration. Then also there's this integrator called CMC Ecosystem in Canada. They help in reducing the biotechnology adoption, so they can give you access to a state-of-the-art CAD and design software. They also give you access to the fab with MPW run and to the labs. They all have the building block for technology advancement, so if you have any need, you should contact them. There's AIM Photonics that has the same thing for the US-based market. So again, AIM Photonics have our packaging technology in their roadmap. We are part of AIMS, as you can see, IBM, and AIMS also give access to integrate photonic ecosystem with all the softwares and PIC foundries, and all this ecosystem is there to enable your prototypes. And there's a red carpet that's go from this prototype to this manufacturing volumes at IBM Bromont. So if you use our technology and process compatible technology, you will be able to migrate on our floor. I also have to mention that we work closely with many universities, and here I will give you an example of the industrial researcher that we have with University of Sherbrooke. This one is mostly focused on a high performance integration and low temperature interconnect for high density packaging and advanced photonic packaging. So, and also for low temperature interconnect. So now that we have closed this ecosystem, those are some entry points to enable this ecosystem for PIC design and PIC fabrication and eventually to manufacturing. But when you think about advanced integration and co-packaging, you have a lot of things to consider. And you really need to have a design for manufacturing and also a design for test, because having some design specific tests and built-in self-tests is very important. So you have many aspects to consider, and of course you're going to do a lot of simulation and measurement. But one thing I want to emphasize is that we have some predictive manufacturing. We do modelings. We have this industry 4.0 that we monitor everything on the line to be able to do some data mining. So it's really at the leading point in advanced manufacturing. And I'm very proud of showing what IBM do in the process management and in the quality and the excellence they can deliver. So in this example here, you have a pretest test C-subs, 8 of them. So those are the optical engine or the transceiver surrounding a switch ASIC. And we will use this as an example case of in the next slide. As you can see from the switch ASIC to the electrical die, those extreme small short reach link, and then you have the ultra short reach between the electrical die and the photonic die of the CSOP. So as you can see, the electrical signal will go high speed to the electrical die. They will be formatted, and maybe have some FEC or other operation, and then they will be modulated to the PDI driver or to be modulated directly on the light and go through the fiber optics. So packaging is critical for success in mind. So when you're looking at this PIC die and electric die, the best way to do that is to have a monolithic integration. As example, in the A and B configuration, where the PIC has all the electric and photonic devices. And this is the base case scenario. In those A and B, the difference is one is an overhang chip, and the other has a little opening inside the substrate to open up the fiber attach or the optical attach region. When you're not able and you need to use another die, another node die, you can use a 2D configuration, but sometimes it's more efficient to have it face-to-face because you can reduce this length. So in the face-to-face, you can even have it in this configuration where the PIC is in a little recess, or you have a little organic interposer that rises the electrical die on the PIC that's deposed on the substrate. Then there's this configuration that I really love is when you have this organic interposer between the E die and the P die. So you still have this very, very short region between the E die and the P die, but you still have this substrate, and you can do a lot of planes and redistribution layer inside this interposer to be able to feed the power to the PIC and the E die within this face-to-face region, especially when this face-to-face region is quite large. And then if you're the best, another way to do that is have a traditional 3D packaging with TSV, not having the E die and the P die one over the other. So those are the kind of packaging integration or how we can integrate a PIC chip in our package. Those are some of the configuration available at our site. So when you look at the consideration for the optical coupling, so there's many interconnects technology that exist, but currently what we believe the best overall solution is really the V-groove, because with the passive alignment, you can go to high throughput, automated, and very scalable process. The assembly complexity very low. The fibers are held by the V-groove, so you have a mechanical and robust attach of the fiber that, and it's a solder reflowable compatible process. It has a low profile, low insertion loss, as we will see in the next slide, over 100 nanometer spectral length, and it's coupled with two polarization. If we look at the switch example, for example, here we have ASIC chips, ASIC chip 51 terabit with 112 gigabit electrical length, so 56 gigabaud PAM4. And if you look at the number of optical fiber you have to put on this switch, for example, if you do an NRZ with 1 lambda per fiber and 1 laser injection, you will need more than 3,000 fiber. But when you split the laser in, you can reduce number of fiber. When you use more lambda and doing multiplexing, you can again reduce more. And when you do the PAM4 and 4 lambda multiplexing, you're now in 300 fibers for this switch application. And this gives you a fiber density of 1.5 fiber per millimeter. For example, if you look at other coherent, you also have some other metric of the number of fiber based on those assumptions. So, of course, the connectorization, you have either to decide, is it going to be a fiber pigtail or integrated connector? How are you going to handle, are you going to have some PM fibers that need to be connected? How are you going to have your fiber escape from the edge density? And you have to consider your connector loss and your fiber management to the front panel in your optical budget. Then how are you going to attach the CSOP to the MCM? Are you going to use a socket or a micro-bridge reflow? And you have many considerations in terms of signal integrity, isolation, beachfront, yield rework, and all the other aspects you have to compare those two. And then the laser source. Currently, the best way to do it for large switch that will be high thermal is to have externally, but you have additional PM fiber to be mounted to the device. So when we look at those figures, what we're looking at, a standard fiber is at 250 micron pitch, so it's a density of 4 fiber per millimeter. And when we include the CSOP packaging that's around it, we're more in the 1.6 per 2 millimeter per fiber. So it's very, very close to what we have seen here. And of course, there was some debate between direct detect and coherent. So of course, coherent, you can you have a better number of symbols per baud. You can send more data, but your wall plug-in efficiency is not as best. The latency is a little bit higher. So yes, you can transmit more data, but you will have a little bit more latency compared to direct detect. So we discussed a little bit about this socket. In the case of a very bit switch where multiple CSOP optical engine have to be included, you really need to think of the overall yield. And if you have, for example, a 98% yield on a 12 CSOP, your overall modules will still be in 80 or up percent. So when you have a lot of optical engine, you maybe better to have a socket. But you have to account clamping mechanism and the configurability, because you will need some real estates to be able to mount those sockets. But currently the socket performance, it does exist at those high speed, but they will induce some cost. If you have a BG reflow, you will have a better configurability. You will have a better signal integrity by design, and you will have a smaller footprint. Well, you will have loss at rework, and this will be a yield risk on your large CPO. So here we have a little image of our silicon photonic reflowable module here with the empty connection. So for the fiber array or single mode solder reflowable coupler, I will describe a little bit more our test vehicle and how it works. You always have on the top right the papers that describe in details. If you want more information, you always can email me. So our test vehicle was a 12-channel test vehicle. We had it one in O and the other one in SCL band. It coupled both polarization T and TM. In fact, there's two now. There's one low PDL, so it's tried the best to couple the two polarization. And there's one low ORL, so it's focused on one polarization, but with extremely low return loss. Both of this coupler is compatible with high pick and place tool, high throughput pick and place tool, and it's solder reflow compatible. To do so, we have those V grooves where the optical fiber will sit in. In front of the V groove, we have the suspended membrane where a metamaterial mode converter is printed. And this mode converter is engineered for max tolerance. And the key for our assembly is to have adhesive partitioning. So basically, we're using a structural adhesive for fiber robustness inside the V groove, such as a fast UV tack. It will provide the mechanical stability and keep the alignment of the fiber towards the suspended waveguide. And we have one optical adhesive that is clearly designed for optical performance and really reduce the stress on this suspended membrane. So for the self-alignment, so basically we will take the optical fiber and they will press and they will fall inside the V groove. So when you do a multicolor analysis of all the tolerances and variability that you have, for example, the fiber diameter, the V groove width variation, the fiber core concentricity, and all those aspects put together in this multicolor, you have this overall misalignment from the variability of the component. And then you can design your mold coupler here at the bottom right of the image to have a very, very good response within this wire. So as you can see here, all our tolerances together make a plus minus 1 micron window for the final alignment from the self-alignment process. So the mode converter has been designed, as you can see the theoretical curve, has been resized to have a 1 micron, plus minus 1 micron acceptance window. So you see the top, this is the nominal, and you have a hardware that was validating with some V groove groove variation, so we can really assess the performance of our coupler. We also have high sensitivity, where any misalignment will translate in very, very high optical loss, and we can easily monitor sub-micron deviation or disalignment. So the main problematic is to take the energy and the signal from a 9 or 10 micron mode field from the optical fiber and be able to place them inside the V groove in 1 micron and have the mode converter be able to collide to the nanowire where the TE and TM mode is done. So here I have a little video that will show the self-alignment occurring. So look at this blue fiber at the right. You see it's totally misaligned, and when it's entered the V groove, it will be replaced within this 1 micron for the mode coupler. Now we even have a better mode coupler at GLOBALFOUNDRIES. They have improved, and they have published that last year in the Journal of Selected Quantum Electronics. And now we have 0.7 dB peak for the TE and 1.4. And as you can see, I also put some of the return loss. So we are in the 30 dB from the optical fiber input, and over the metamaterial, as you can see, we are below 55 dB in the return loss. This is very, very, very good. And here you have some photo of the patterning of the metamaterial on the GF mode coupler here. So here's some reliability data. So first of all, we have a reflowable demonstration. We also have thermal cycling. We did first a Telcordia-like minus 4085, and then we add another 1000 cycle of JEDEC-like. So it has a cumulative of 2000 thermal cycling. So this is very, very good. We did also the damp heat. As you can see, this is using high sensitivity hardware. So we're within the error of measurement. This is the measurement before and after. So it's the delta, and zeros mean no change. And as you can see, we have 0.2 to 0.4. So we're within the measurement error for the change after the stress. Now here a photonic flip chip assembly example. So this is a product that we had for us optical switch, and we had the test vehicle. So basically it's a substrate with an opening so we can do the fiber attach. It was a nickel coated lid, and we had a photonic chip with a 200 micron pitch interconnect, and we had the optical V groove from GF with capillary underfill. And as you can see, the repeatability, this is the real average transmission loss for the TM mode per facet. As you can see, we have a 1.6 dB in average, and here you have a little histogram of the, so we're mostly between 1 and 2.5 with a very good probability. This is the test vehicle. And we were using formic acid flip chip bonding because we need a fluxless solution to maintain the groove facet cleanliness and the suspended waveguide integrity. And we use a tacking fluid adhesive material. And we didn't see any voiding cracking the EMC or the solder, and this is available at Bromo. So we have a production formic acid furnace at the main plant, and we also have a small R&D oven lab, formic acid oven in the lab for process debugging. So this is the main question: is should we do fiber first or fiber last approaches? So here we'll discuss a little the pro and cons of either. So when you're doing fiber first approach, of course you're going to have early optical interface protection, since the fiber will be glued there, and it will protect this assembly region, and you will do the fiber attach in the best condition. And this enables also you to test and perform subsequent assembly of non-good sub-engines. But still, you will have to manipulate this fiber stub, and you cannot do a very good strain relief on this sub-engine. And how will this fiber stub pigtail impact the flip chip or downstream process is some of the cons. When you do the fiber last approach, then you're more compatible with a standard microelectronic assembly, and the lid can provide a very good entry for strain relief, but you will need extra precaution for the optical interface protection, for example, as using formic acid furnace. And you also need a fiber attached with either a cavity in the substrate or the chip that will be a little bit in overhang. So here I have some animation to explain how this attach process works. So first you have a robot handler that's grabbing the fiber array and grabbing also the glass buffer with the pick tip. This is a UV transparent pick tip. So basically it will enable UV adhesive. So we will dispense all the needed adhesive at the various locations. We will do all the curing of the strain relief, mechanical and optical. We will do a quick UV tack and the batch process finish of the cure later on to dismiss the high throughput tool. So the robot will place the fiber array inside the V groove, and the pick will push it. So the self-alignment process will occur. At this point, the quick UV tack will occur. It's a less than 5-second tack. and then the cure is finished in a batch tool process after that. Then you have also to consider optical connector, and we truly see that the connector size are quite huge. And when you look at the drawings of a ferrule next to a package, you realize that those are huge. So we really need smaller size, and ideally we'll need solder reflow compatible ferrule, because it's really changed the integration chain and how you can assemble your photonic devices in your systems. We also need low loss single mode for 1x16, 2x16, and 1x24 fiber. There's work currently being done on having 80 micron fibers on a reduced pitch. On the big chip, and we'll love to see that also from this on the ferrule side. And we have to include PM fibers to inject light. So we have a special component that have a mix of PM and single mode fiber inside. And here we have a little example when you have 4 PM laser input and a standard single mode fiber for IO that are clocked together inside the empty. And we are doing that. And of course, you have to consider efficient shipping and expedition of the fiber component and the photonic modules, because having those pigtails and optical phase, you need to protect them, you need to secure them in the package. So those are all elements to consider. So we have discussed about the fiber V-groove attach. Currently those chips are available at GLOBALFOUNDRIES. We're one of the certified OSAT for this technology. Now we will discuss more about the compliant polymer interface. So this is another coupling technology using adiabatic coupler. It's enable a denser pitch up to 25 micro at the chip interface, and there's no need for deep V-groove or wet etch process. And the mode cooperator is more simple, and since you're using a compliant material, you have less chip package integration risk mitigation. And we have present early this year in January a very good paper on this technology, so you can go see all the results and the reliability demonstration of this technology. Currently, we're enabling a new foundry, so it's IMF, so Advanced Macro Foundry. So we're currently working with them to. So we have O-band and C-band loopback test vehicle, and we're currently working on the functional devices. And as you can see here, we have our polymer waveguide, as you can see at position with the optical adhesive. And here you can see some of the structure of the IMF. And there's those are new results. They are submitted for publication, so they will be published maybe later this year. I will just give you a quick glimpse of the new results that we have on this new foundry. So this is the insertion loss per facet. So this is from the single mode fiber to the polymer to the PIC. So it's include all the loss. And here you have your O-band 100 nanometer coupling. As you can see, all the channels. So it was a 6 loopback test vehicle, a 12 channel. As you can see, we're in the better than 1.5 dB in the coupling loss over all the range. And we made 48 components. And here you have the absolute insertion loss per facet. And you have a little histogram of the population. And this is using our polymer and the ferrule. So we're using self-alignment for the polymer to the chip and the polymer to the ferrule. And we use active alignment between the empty to the polymer empty to remove this empty loss and just focus to have the polymer and the adiabatic coupling loss to the devices. So we're very excited. Those will be presented, so you can go see those results, and it will be available at IMF. So in conclusion, co-packaging is required for the next generation switch. Design for effective manufacturing is key for the success, and we have shown today some co-packaging toolbox for single mode optic assembly. Those processes are wavelength demultiplication compatible. It's leveraged microlinking know-how and infrastructure, and it's compatible with high throughput facilities. So here you have an example. I have still to say a final word on power efficiency with data protocol, because we're talking about those large CPO switch and those. So we need those high bandwidth processor that using drive optics they will be limited by thermal power you design, and they will consume too much power. So maybe having a rapid on-off will enable more efficient power usage, and we can have the same. IBM has demonstrated those amazing results. So 8 nanosecond power on and clock data lock, always power on of 2 picojoule per bit, a standby power of 5 milliwatt. So very, very interesting. We have a prefec of 10 minus 12 prefec. This is very good. 2.2 joule at NRZ, 1.1 picojoule at PAM with the PAM4. So this is very interesting. So those are some, and if you contact me, I can route you to the IBM team about that. So thank you very much to all our team. I will now pass the microphone to Vikas from GlobalFoundries. So we will give you more details about what GlobalFoundries Photonics offers. Thank you very much.
Thank you, Alexander, and thank you, Jim. Good morning, everybody. My name is Vikas Gupta. I'm the Director of Product Management for Silicon Photonics at GlobalFoundries. And I would like to thank the Consortium for Onboard Optics and the DuPont team for this opportunity to participate in this webinar. The genesis of Silicon Photonics program at GlobalFoundries in large part started with our acquisition of the IBM microelectronics business. And hence, I'm very happy and excited to share this webinar with my friends at IBM Bromont. So I plan to cover two main topics in the 15 minutes or so that I have. I wanted to give you all an introduction to Silicon Photonics at GlobalFoundries. And then I plan to cover some key industry differentiating features that we're working on. And then, of course, I will close this, giving some context on how all of this fits into the co-packaged optics ecosystem. Next slide. So Silicon Photonics wafers at GlobalFoundries are being processed currently at two facilities at GlobalFoundries. This is Fab 10 in Fishkill and our Fab 8 in Malta. Fab 8 is sort of our end state manufacturing facility for Silicon Photonics. It is our most advanced fab, running at 12 nanometer and 14 nanometer FinFET technologies with a capacity to run around 500,000 300 millimeter wafers per year. And the reason I wanted to show you all this is to just show the commitment that GlobalFoundries has to Silicon Photonics as a technology. Our technologies will be running on a 300 millimeter wafer. Next slide. So I just wanted to just sort of go back to the basics. The growth of the semiconductor industry has been dominated by electronic components and circuits. And we're used to talking about the transfer and manipulation of electrons using active components such as transistors, passive components such as resistors and capacitors. And similarly, on the photonic side, we talk about manipulating photons using active components such as lasers, modulators, detectors, passive components such as waveguides and spot size converters, and input-output components such as laser trenches to place lasers into, fiber V-grooves, as Alexander mentioned, and grating couplers. While indium phosphide has been the material of choice in the photonics industry, Silicon Photonics is becoming increasingly interesting due to its use of the silicon ecosystem that has already been established on the microelectronic side. It brings with it significant advantages of the reduction in packaging costs, higher levels of integration, lower power consumption, and significantly, the ability to perform wafer-level testing and packaging. Next slide, please. So at GlobalFoundries, we have a 90 nanometer and a 45 nanometer photonic technology with a plan to address the communication market, including datacom, telecom, and 5G networks. We are already engaged with customers for chip-to-chip communication using co-packaged optics, and customers wanting to use Silicon Photonics for other applications such as quantum and photonic computing, time-of-flight sensors, and LiDAR. Some of these markets are ready right now, and some of them have longer gestational periods due to qualification requirements, but this sort of forms the market segments that we are trying to address with our technologies. Next slide, please. At GlobalFoundries, we are in the business of selling solutions and hence the Silicon Photonics business line actually consists of two pieces. One is the RF SiGe technologies to address the electronic components, which match up with our photonic solutions for data center applications. And of course, this talk will be focused more on the photonics IC piece. Next slide. So I wanted to give you all sort of a flavor of the feature set that we have on our leading edge photonics technology. So 45 SPCLO, or CLO as we call it for short, is a monolithically integrated RF CMOS technology along with photonic components. Going clockwise from the top left corner to the bottom right, one can see the photonic components such as modulators, photodiodes, phase shifters, mux-demux solutions. At the bottom, sort of 6 o'clock area of the slide, you can see almost MEMS-like components such as a trench for a laser attach, V-grooves for fiber attach, and grating couplers for on-wafer testing. And that is a facility that we provide to customers where we are actually able to collect fairly large amounts of data, statistically meaningful data at wafer level for photonic components. On the left side of the chart, you can see our electronic components, which is the RF CMOS transistors, which can be integrated into TIAs, drivers, etc., and spiral inductors. We also support a PDK, a fairly comprehensive PDK, which includes P-cells and models for these components. So with that as a background, I wanted to cover 4 features, sort of differentiating features that we're working on, and it sort of ties back to the slides that Alexander showed. So next slide, Alexander. So the first part is the monolithic integration. So we, as I had mentioned, we have integrated a high-performance 45 nanometer RF SOI technology with the photonics. The monolithic approach has the advantage of reducing packaging complexity and cost. And furthermore, one can squeeze out more performance out of the transistors due to the fact that you have reduced parasitics associated with packaging and ESD. So note, because the transistors are monolithically integrated with the photonics, the connection actually becomes an internal node, and so you actually eliminate the need for ESD. So while this technology may not have the fastest FT, you can still achieve fairly high data rates with this technology. Next slide. We're also enabling an on-die laser attach, and this is done by creating a trench on the wafer and aligning a DFB laser using fiducial marks on the pick and the laser. This is done passively using a high-precision pick-and-place tool. Again, this is another differentiating technology which has the potential of reducing packaging costs and also packaging complexity significantly. Next slide. This slide refers back to some of the work that Alexander was showing. We have enabled V-grooves for fiber attach, and the V-groove is created by doing a crystallographic etch, which allows for the self-alignment of passively paced fibers with a suspended spot size converter. And if you refer back to Alexander's chart, he's gone through a lot more detail on this front. So while this technology is interesting for datacom applications, it really starts to shine for co-packaged optics, where you have fairly large arrays of fibers that have to be attached passively to the die. Next slide. Here are, Alexander had a chart where he was showing the different options, and then and correspondingly on the GlobalFoundries side, what I wanted to show you all is sort of the 2.5D packaging solutions that we are working on to make it compatible with solutions that Alexander had talked about. So on the top left, you can see the work on some copper seed pads, which are compatible with a laser cavity, and you can actually see the routing going into the cavity on the top left. On the top right, you can see similar copper seed pads, which are compatible with V-grooves. On the bottom left is sort of the copper pillar bump technology that we're working with, which are compatible with V-grooves, and this allows you to flip chip a PIC die on a laminate. And then on the bottom right, you can see sort of integrated together copper C pads, which have an on-die laser and also are compatible with the V-Groove technology for fiber attach. So I wanted to, this is sort of my final sort of differentiation slide, and I wanted to spend some time on this. I talked about the laser attach, the fiber attach, the 2.5D integration, the monolithic integration, and this sort of compiles everything together as solutions that our customers are looking into. So earlier this year, Facebook and Microsoft have released a standard towards trying to standardize co-packaged optics. And this document was published through the Facebook site, and it provides some standardization associated with a optical engine, which is shown on the top left, which then integrates on a router chip where you can see the optical engine sort of surrounding the router chip or the FPGA. While this has been sort of an early attempt at trying to standardize, you can see that companies that are trying to read this document and come up with solutions which meet those requirements actually have fairly different solutions, ranging from a silicon interposer to a fairly complex dual-side organic type of packaging. As a foundry, our desire, of course, is to enable our customers to allow for this sort of work. But again, there's a lot of work to be done in this industry to actually come up with a standardized package to address co-packaged optics. And that is something that I think the ecosystem associated with foundries, OSATs, OSATs such as IBM Bromont, our end users, which are the data center operators, all need to work together to sort of come up with a standardized solution for co-packaged optics. So this is sort of my summary slide, and then we can open it up for questions. At GlobalFoundries, we are committed to silicon photonics. We are using a 300 millimeter wafer fab for production. The intention or the goal of silicon photonics at GlobalFoundries is to provide a differentiated solution for our customers through the reduced, through unique features such as monolithic integration and unique features associated with packaging. We do feel that these allow the reduction of interconnect parasitics, the close proximity of the CMOS, and silicon photonics allows for higher bandwidth and higher density of transceivers. And we are working with various customers to provide differentiated solutions associated with co-packaged optics as part of our business. So I believe that is my last slide.
All right. Thank you very much, Vikas and Alexander. That's a tremendous presentation, a lot of very impressive technology there. At this point, I think we're ready to do a quick poll of our audience. So Julian, if you could queue up our poll, it'd be interesting to see what people are thinking in terms of markets and timelines for this kind of technology. I'd also like to encourage anyone and everyone to submit their questions for our two panelists. We have a number of those questions coming in already, and we'll do our best to answer them as quickly and as best we can. So while we wait for that poll results to start coming in, Alexander, I'd like to jump in and ask you first a quick question about the example that you gave of the optical switch. Could you tell us more about that project?
We are involved in those kind of product. I cannot say much, but we're working. So those are like the ground rules. I published early this year a very exhaustive paper of all the requirements and challenges and consideration you have to take in account in designing those kind of switches in terms of a packaging perspective, of course. What can I mention more? Currently, our main goal is to use 4 lambda. Basically, we will graph on standards, Datacom standards for wavelength. This slide, are you referring?
Yeah, exactly. So,
Yeah.
just curious how far along that project is, and what, perhaps if you could say anything else about the customer or
I cannot disclose much. I'm sorry currently, but we're working with many customers on kind of application. We also work on those application of optics in machine learning and AI. There's a lot of people interested in photonic AI, so we have a lot of work in that. But for this CPO package, this slide was mostly listing all the consideration, and it was mostly in phasing that the number of fibers, optical fiber needed, is quite huge in those kind of products. Because even with splitting the laser and multiplexing 4 lambdas, you still need over 300 fibers. So this is where scalability and doing multiple connection at the time and doing those fiber array assembly is really, really important. And it's a game changer. And we also have solution to include PM fibers inside the arrays. So we can very, very easily assemble PM fibers in the same manner, since they're already pre-clocked and pre-aligned within the system.
Excellent. Do you have already any data supporting reflow compatibility for the V-groove based fiber attached solutions, or is there any possibility that you'll find a suitable epoxy?
Yes, we have demonstrated reflowable. We even demonstrated reflowability on the full flip chip module, so the complete assembly, not only the fiber attached, but with the PIC inside the package with the flip chip, photonic chip, was reflow compatible. The main problem with is the ferrule. So currently our solution is to have longer pigtails and protect the ferrule from the heat, because it can support some heat, but not too much. So this is our main solution. We work with suppliers to have, and we are evaluating many vendors for reflowable ferrule, and we have some candidates, but they're not elite grade. They're more like a standard loss ferrule. So yeah. So solder reflow has been demonstrated for a fiber attach. It is also demonstrated for a full assembly with a co-package photonic chip. So it is demonstrated. The main problem that is missing is having the ferrule that is solder reflow compatible. And currently we are protecting them or doing direct heating and other strategies, basically protecting the ferrule from the heat. These are current.
Is there a baud rate at which coherent becomes more efficient than direct detect?
The main advantage in coherent is because you can put more samples. So the bandwidth reach metric is huge. You can send a lot of data. So there is some advantage. We will see how the market. Currently, the direct detect can be faster. It will have a lower latency than having the complex signal processing and recovery of the sample of coherent photonics. But I believe as the bandwidth need will increase in the future, coherent might take more and more place inside the data. We will see.
Okay. Another thermal question: is the MT ferrule reflow compatible 260C? And this refers to your 2019 Photonic West paper that our audience members saw.
Yeah, we did a lot of work, but we don't have elite grade ferrule, so we only have more standard grade. And as we have seen, for example, the 1/8 ferrule was quite good, but when you try to do 1/12, the exterior fiber were a little bit worse. So no, the reflowable ferrule are not ready in the industry, not for the MT. There exists for LC, but not for NT. In the single mode. That's the other thing, reflowable and single mode together. So yeah, so we hope, because it changed how you can integrate your optics and assemble your devices, and it gives you a lot of integration shame if you can support reflow.
Okay, great. Another thermal question here, and implications for the packaging, and whether you've thought about liquid immersion technologies. Would you be able to take these kind of packages and put them in
Yeah, like with dielectric, liquid to thermal.
Yeah.
Yes, we have with the, I don't know what I can share. We have a project with the university on that, and I know that their IBM is working on that, but I cannot disclose much.
Okay. Regarding PM access alignment, how it can be made to a PM fiber array, how is that done?
Yeah, so currently basically they're clocking the PM at the two portion. So one in the empty and one closest to the fiber attach. So basically you will have a holder that will keep the clocking of the PM at the V-groove assembly site. And we are able to monitor up to a 3-degree conservation. So it's a 20 dB expansion ratio between the polarization. And of course, we do have a feed contact with active alignment. So we can do PM clocking to 0.0001 degree for extremely high PM clocking and things like that. So because there's some products that need very, very high, but the main strategy for the V-groove is to have them pre-clock at both sides, at the MP and at the fiber V-groove at that side, and clock and lock in place. So it's very compatible with our assembly process. It's like a regular fiber because it's already pre-clocked.
Okay, great. 2 more quick fiber questions here, and then we'll jump over and give some to Vikas. So regarding the 80 micron fiber needs, could you comment on bend radius, ideal OD and bend radius?
Yeah, in fact, there are fibers with lower bend loss or zero bend loss. Typically, the main strategy is to reduce the mode field. So having a more micron fiber, the main advantage is the density you can put on your pick tip. It's amazing because even 250 micron pit for the optical fiber takes a lot of space on the pick chip, and we need some space also to have all those underfill fillet and all those bleed out and adhesive space on the chip. So this takes a lot of real estate. If we can scale to smaller fibers, we can have denser pitch. We'll take less real estate. We will be able to include more fiber beachfront of the chip. So I know we're working on 80 micron. I know GLOBALFOUNDRIES are offer them eventually, and I know we will see them. So we are very excited about those 80 micron, but it's starting.
I know you had that slide showing, things that you wanted from the fiber side. Yeah. So in terms of the fiber array coupling versus polymer waveguides, which is preferred in the mechanical robustness and optical characteristics?
So the V-groove currently is our front runner because GLOBALFOUNDRIES is really mature. We're ready for production basically at this point, and it's very processed. We do that day-to-day basis, doing those kind of fiber attach and very user hardware. So it's a really mature technology. We see the polymer maybe further down the road when the density of the I/O port will be higher. And there's some application that needs, for example, chip-to-chip communication might need some kind of polymer waveguide. This kind of coupling technology may have some advantage there. So the polymer is really there where higher density, higher bandwidth is needed. We see that further down the path. And we're currently doing this functional demo at IMF. So we're very excited about that. It will be offered, so you will be able to test.
Okay, great. Well, thank you. I know we're coming up soon to the top of the hour, but we will be extending this session to take as many of the questions as we can. So Vikas, this one goes to you about the GLOBALFOUNDRIES roadmap slide. And maybe you can also see some of our poll results by this time. So the question is about different market segments for silicon photonics technology. Could you comment on that and timeframes?
Yeah, so I think, as I mentioned, we right now have 2 technologies, the 90WG and 45 CLO. the idea is to start off with these high volume market segments to establish sort of a beachhead, if you want to call it that, and use that sort of base technology to address other market segments like photonic computing, or time-of-flight sensors, and automotive LiDAR. There is always, as the industry matures and there are needs for higher data rates and silicon photonics starts to enter other applications, we will continue to expand our roadmap. And I think from a foundry perspective, the idea is to use sort of the base technology, and if it requires, add more silicon nitride layers, different ways of coupling. So again, the roadmap is a living sort of living aspect of any foundry, and the intention is to start off with the base, try to get the market addressed through a vibrant technology, and then as this expands into additional markets, understand those requirements and sort of include it on the base. So I think on the top right, it's a bit of an eye chart, but I have sort of given a view of things that we are thinking of with respect to a roadmap. So we start off with a base photonics technology, maybe address O band, next address C band, further going out into L band, and then also to the point that Alexander was making, for these technologies to be compatible with higher density fiber arrays. There's this need of making the V grooves at a tighter pitch. So those are aspects of any roadmap, any foundry, whether it's microelectronics or photonics, we have to keep on top of, and we will.
Okay. It'd be interesting at this point to see some of the results of our poll. Julian, do you have those results? Here we go. So Vikas, what do you think? Does this kind of align with the Global Foundry timeline?
Yeah, so I think, I had specifically asked for, like sort of production in the first question. Hopefully everybody sort of got that nuance. And I think this is an expected sort of result. And then for the second one, again, I think it sort of reflects and it sort of validates the Global Foundry strategy, where you can see that a significant amount of application on silicon photonics is with the datacom, datacom industry. More specifically, I would say, sort of the within the data center market, IDC market, which is the one sort of dominating on silicon photonics side. And then, with respect to LiDAR, that is what I was referring to as technologies where silicon photonics is going to enter in a big way, but it's just one of those technologies which has a long gestational period, just because of automotive qualification requirements and the sort of ADAS industry itself. So that will take some time. So these results are actually, they sort of validate the strategy and it gives the Global Foundry strategy credence to what we're doing.
So I think the next question probably ties right into this, and that's to talk about the yield and the expected yield that you might be seeing, and whether that is in fact the driver for the data center interconnect business. Is it because the yield improves so much that it becomes attractive in this segment?
So it's actually not just the yield. It is the higher levels of integration, the fact that, I had mentioned when we were talking about some of the features of 45, the fact that we have grating couplers, a lot of the test can be done at wafer level. So you actually, through that, it implies you will probably get better yield, but there's a lot of integration work that can be done at wafer level. A lot of the laser attach can be done at wafer level. The die attach can be done. So you're basically scaling out packaging to sort of microelectronics type of levels. And I think Alexander sort of referred to that I think the goal of this industry to make it a viable solution is to sort of address sort of the OSAT solution rather than coming up with very unique and custom solutions with respect to packaging, try to sort of shoehorn it into an ecosystem which already exists around microelectronics. So I think it's a, so there are some of the things which are being put in place which will help with the yield, but a lot of it is also just because of the wafer scale and the ecosystem that you are sort of fundamentally changing, versus these hand-picked modules and trying to do a lot of automation around packaging and test.
Could you talk about the laser attachment on silicon, the yield that you see there?
That is sort of a program that we are driving pretty hard. Again, I can talk about it in more details once a particular customer is interested and wants to use that technology, but it should be ready for prototyping before the end of the year.
Okay. Let me toss the same question over to Alexander. If you could, comment a bit on yield that you see it for fiber attachment.
Yeah, so we have a fiber attached that's very, very good yield. Of course, currently we are more like inspecting all our components, and we're doing more verification than usual because we're still in the development phase of this program. Eventually we will have more we have limited data because we only build 100 parts. I would love to see 1,000 or million of those parts built before be able to disclose real yields, because this is a very new technology. So currently what we see is we're able to package and assemble GlobalFoundries dies. We're able to do flip chip photonics with them, and we're able to yield them quite good. So we're very excited, but we don't have enough data at this stage to be able to I say commit to a yield. We're too soon. We need to have the design fix and some experience on the volumes mentioning yield.
Okay. Here's one audience member who asked me, how do you do the self-alignment of the compliant polymer interface?
Oh, we're using the same self-alignment technique. So basically we're having, on the polymer, we have some ridges that are, because polymer is photographically defined for the waveguides and those ridges. And basically we have some little very, very small right edge, less than 15 micron depth. And the ridge will fall inside those, so it will perform the self-alignment. In the case of the adiabatic polymer, we can have up to 2 microns offset between the polymer waveguide and the photonic nanowire, because the polymer waveguide is so huge compared to so we're doing self-alignment at the peak, and also we're doing self-alignment from the polymer to the ferrule of the polymer.
Okay. A question, pigtails versus optical connectors. Which way do you see it becoming the main trend?
This is a good question. Pigtails have some advantages. If you have them long enough, you can resplice a new connector if one is faulty, things like that. But in terms of manufacturing, I can tell you about the spaghetti syndrome and all the issues that can have those long pigtails, and you have to manage them inside a tray, replace you empty, so it's when you dock your tray, it connects to the optical connector connect, and you're able to test the device. So there's many advantages of having those embedded connectors. But currently having pigtails is more vanilla for our process. But we are working on this connector. Currently our integrated connector is working, but it's not reflowable compatible. Our main strategy, and I can disclose because we have an IP protecting it, it's basically we're bending the fiber inside the connector. So basically we'll create a radius of curvature, a kind of ellipse of the fiber. So the fiber with the CT change of the package, with the thermal cycling or the reflow or the bending, the optical fiber bending, the radius change will accommodate the CT mismatch. that occur inside the package, and we're working on that, and we hope to publish some results next year at DC.
Excellent. Back to Vikas. Could you talk about wafer testing of PICs? How do your designs permit such wafer testing?
So we have, as I was mentioning, the standard way, as Alexander was talking about, of doing sort of light in, light out. You can either put the laser on the PIC, or have V-groove interfaces to your fiber. But again, the fiber attach is done at the die level. In order to do wafer level testing, we do have an ability of doing electro-optical testing on the wafer. There's a sort of a specific pad cage that we sort of offer customers, which have grating couplers for interfacing the light, and we can do the testing of these structures at wafer level. And so we're able to generate almost similar to on the microelectronic side, where foundries offer wafer acceptance criteria and a list of parameters. We can offer similar sort of services on photonic components, where as part of that pad cage, you can draw cutback structures in your GDS, and we can fabricate them.
Okay. Another question for you. You had a slide that showed or compared indium phosphide versus silicon photonics. What's stopping indium phosphide to be co-packaged with high-powered ASICs? Is it a lack of the monolithic thermoelectric coolers?
So it is partly the scale. We're talking about, for example, a 300 millimeter wafer of silicon versus maybe 2-inch, 3-inch wafers of indium phosphide. Then there is a lot of the complexity associated with driver circuits for indium phosphide lasers and modulators. So a lot of it is, when you look at, for example, the chart that Alexander showed, which with the number of the photonic engines surrounding your ASIC, you start to realize how compact that space is, and higher levels of integration will always get you there quicker. So I think indium phosphide as a material may be superior, but I think the integration aspects of silicon photonics sort of help with that aspect.
Okay. Alexander, IBM demonstrated both direct V-groove fiber types as well as polymer interface type connectors. Which one do you think the industry will adopt?
Both, but at various point in time. So I believe the V-groove technology from GlobalFoundries will ramp up significantly, and because the technology is very mature, and what GlobalFoundries is doing with the chip is very, very good. And they have a lot of very good photodetector rate are crazy. The waveguide loss are very, very good. When you look at the global picture, GlobalFoundries chips are very, very there. It's really great. And when you do the right packaging with the right OSAT, it can be very interesting. So I believe the V-groove will emerge first and will grow, and the polymer will catch later when the denser application, or maybe some people that IMF want to spin out and have the more polymer IO, optical IO. It might be suited there, but it will be V-groove, and then the transition will go to the polymer. It's my belief. I'm not there. We will see what the industry will say.
Okay. How much power savings can you achieve compared to pluggables? What about baud rates and signaling? Does it have a retimer or direct drive?
Yes. In fact, you save a lot, close to 50% because you're losing so much. A high speed electrical reach is fading so fast. So when you're trying to reach, you will have those retimer, and it will drag a lot of power. So when you have those high speed signals, you have to have very, very close reach, as we have seen. So this is why the power management, and we're forgetting all application that can benefit having this high bandwidth optical interconnect. Think about all those machine learning AI chips that need to learn a tremendous amount of data. How can you feed those terabit of data to an AI chip so we can learn and train? And so those kind of optical connection will be needed in those kind of applications as well.
Okay, here's a question about very high count fibers. Even with RAM 4.4 technologies, we still need 320 fibers. What's your suggestion on how to manage those fibers?
Yeah, fiber management is very touchy, and having all those pigtails and how you display them and how you handle the device in the manufacturing process with all those pigtails is very difficult. It brings some challenges. So yes, so high fiber count is really where we shine because of our fiber array assembly technology, and we are looking at those issues, and we have some solution. But we didn't yet build the maximum we built was 98 fibers so far, but we might at the end of this year see our first 500 fibers. So it's very exciting. But yes, large number of fiber is an issue, and I call it the spaghetti syndrome.
So it's maybe not just a challenge, it's an opportunity as well, right? Because the fiber management is actually where this technology will shine.
Absolutely, yeah.
Yeah, yeah. So Vikas, could you talk about the GlobalFoundries Silicon Photonics PDK? Is it different from a CMOS electronics PDK?
That's an interesting question. So I'm going to answer it in this way. So if you sort of go back to how people have traditionally done sort of photonic circuit design, you know, a lot of times they start off with some sort of numerical or RSoft type of simulations where they're simulating the device. And then once you've simulated the device, you're basically placing a layout of that structure on your circuit and connecting it up with waveguides. So I think, you know, that's sort of been the traditional approach, but the downside of that is that you have to, the designer, the circuit designer also has to be sort of a device designer. And so that has sort of been how, you know, traditionally people have laid out, you know, these circuits. From the GlobalFoundries side, we actually are trying to change the paradigm, and we want to sort of change, you know, follow the same sort of levels of abstraction in the microelectronics industry, where a circuit designer doesn't necessarily have to know, you know, the device details. They're basically placing out a symbol of a known characterized device. So I think what we are trying to move towards from an industry perspective, or at least our PDK perspective, is put together a PDK which is almost microelectronics, where we have, you know, pre-characterized P cells for a customer to be able to actually do schematic-based photonic design, do sort of LVS checks, and sort of work towards a microelectronics type of circuit design of photonic components, rather than you know, just placing structures without you know, having to have the device knowledge while building these circuits together. So the GlobalFoundries PDK has, you know, in addition to the sort of the CMOS type of P cells, also has photonic components, pre-characterized photonic components, if a customer chooses to use those.
Okay, excellent. Well, we've certainly had just a tremendous number of great questions coming in, and unfortunately, we're not going to be able to get to all of them today, but we will try to answer them online. And finally, I just want to thank our panelists. Alexander, thank you for joining us today. That was you know, tremendous amount of information you delivered, and you know, I think our audience is very appreciative of that, and same to you, Vikas. Thank you so much for joining us.
Thank you, everybody.